Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Geometrical, cis-trans, isomerism in cycloalkanes arises when two or more ring carbons each bear two different substituents, creating restricted rotation and the possibility of substituents being on the same side, cis, or opposite sides, trans, of the ring plane. Moving on to the next step. Identify the compound. The structure shown is 1-methyl-4-bromocyclohexane. Carbon C1 bears a CH3 group and H, and carbon C4 bears a Br atom and H. Both substituted ring carbons have two different groups attached, one substituent plus one H, satisfying the requirement for geometric isomerism. Moving on to the next step. Determine possible geometric isomers. For a 1,4-disubstituted cyclohexane with two different substituents, CH3 and Br, two arrangements are possible. Cis-1-methyl-4-bromocyclohexane, CH3 and Br on the same face of the ring. Trans-1-methyl-4-bromocyclohexane, CH3 and Br on opposite faces of the ring. And for the final step, check for symmetry identity. In 1,4-disubstituted cyclohexane with two different groups, CH3 is not equal to Br, the cis and trans isomers are distinct, non-superimposable structures. Neither is identical to the other, and neither is a meso compound, since the two substituents differ. So both are valid, distinct geometric isomers. Count total geometric isomers. The compound itself as drawn represents one form, either cis or trans. The total number of geometric isomers possible for this compound is 2, one cis and one trans. Why other options fail? A. 0. Incorrect. Geometric isomerism is possible because both C1 and C4 carry two different groups. C. 3 and D. 4. Incorrect. With only two stereocenters in a simple 1,4-disubstituted system bearing different groups, only cis and trans forms exist, giving exactly two geometric isomers. Therefore, the correct answer is B. Therefore, the correct answer is option B.